So at the end of the last clip, we introduced a notation for a so-called coordinate vector. And I gave the impression that coordinate vectors were a generalization of geometric vectors because they allow you to work in higher dimensions than simply just two-dimensional space or three-dimensional space. But I didn't really justify that. And what would be required to justify that? I have to give you a method which would convert any geometric vector in R2 or R3 to a coordinate vector. And that's at least the first part of what would be required. And that's what we're going to start with. So that's the first claim, that geometric vectors are also coordinate vectors. That's what it means for coordinate vectors to be a generalization of geometric vectors. So in particular, here's where the method starts. If you have a geometric vector v, and if I write this down as you see right here, what I'm really saying is that P is the initial point and Q is the terminal point. So may be written as, and then it just trails off. So we're going to finish that sentence, and that's the idea, is that's going to give you a way to express this geometric vector v as a coordinate vector. Now, how are you going to do it? Well, it depends on whether this is a geometric vector in R2 or a geometric vector in R3. So let's start with the case where this is a geometric vector in R2. So there's two different cases. This will be the first one. So I'm going to start over here so I have plenty of room. We can do the following. We can write the geometric vector v, we can write it as a coordinate vector. And the first coordinate is going to be, well, and it's going to be, in terms of a formula, not all of the portions of which I've written down yet. So this won't really make complete sense until the very end of the sentence. But the first coordinate of v, expressed as a coordinate vector, is going to be x2 minus x1. Now, what are x1 and x2? I'll tell you by the time we finish this sentence, that will be answered. The second coordinate of v is going to be y2 minus y1. So this is how you can write the vector v as a coordinate vector if p and q are both points in R2 given with the following coordinates. So I'll say where p is the point x1, y1. So this initial point p, it's a point in R2 with a first x coordinate of x1 and a y coordinate of y1. And then the point q is going to have coordinates x2, y2. Okay, so these are in R2. So if, again, this is what you would do if you were dealing with a geometric vector in R2 and you wanted to convert it into a coordinate vector. Just identify what the initial and terminal points are in terms of their coordinates in the Cartesian plane, and then use their coordinates in this formula to write down what was originally a geometric vector, but now you're writing it as a coordinate vector. You write it down in this fashion. So that's what you'll use in R2. But what do you do if your geometric vector v is in R3? How do you turn that into a coordinate vector? We'll just use the same idea. The only difference is your initial and terminal points will both have an extra coordinate, and you'll use those coordinates to define the third coordinate of the geometric vector v, which you are now trying to write as a coordinate vector in R3. So let me spell that out. So if your geometric vector v is a vector in R3, this is how you will write it as a coordinate vector. And same as before, I'm going to write down the formula, and then not all of the parts of the formula will have been introduced until the sentence is complete. So here's how it goes. So you'll have x2 minus x1, y2 minus y1, z2 minus z1, where p, in this case, if the geometric vector v was a vector in R3, that means the point p has three coordinates. So we'll label them x1, y1, and z1. And the point q is also going to have three coordinates. So we'll label those coordinates x2, y2, and z2. And so these are points in R3. Okay, so if that's the case, well then you can compute, or not compute, you can express the geometric vector v as a coordinate vector in this fashion, right? Because if x1, y1, x2, y2, those are all just numbers. So if you plug them into this formula, you've got two coordinates. You've got a first coordinate and a second coordinate, which means that if you have a geometric vector in R2, this will tell you how to convert it into a coordinate vector in R2. If you have a geometric vector in R3, well, then that means x1, y1, z1, x2, y2, z2. Those are all just real numbers, right? So if you plug them into this formula over here, you're going to end up with a coordinate vector in R3, because this is your first coordinate, your second coordinate, and your third coordinate. So that's how you can convert geometric vectors into coordinate vectors. Let's just let's do one example. Let's say I had a point P given as follows. Let's do an example in R2. So let's say P is the point 2, 1, and Q is the point 3, 0. Well, if I wanted to, and I'll use it, just to be different, I'll use the letter U. How about, let's say if I write down the vector U, and I want it to be the geometric vector that has initial point P and terminal point Q, well, then what? Then I can write down U as a coordinate vector. So I'll say this may be written as the following. I can write the vector U, and then just follow the recipe, right? You've got initial point P and a terminal point Q, which are given by these 2 points. So just follow this formula. Your first coordinate of when I write U as a coordinate vector, I'm going to follow the V, right? Because I called it U, but in the formula it was based on V. So you're going to take the first coordinate of your terminal point and subtract the first coordinate of your initial point. So the first coordinate of U as a coordinate vector is going to be 3 minus 2. Now the second coordinate, if we follow this, we're going to take the y coordinate of our terminal point and we're going to subtract the y coordinate of our initial point, right? Because that's where these 2 numbers came from. So we're going to take 0 and subtract 1. So we'll have 0 minus 1. And what does that give us? Well, that'll just be 1 and negative 1. So here's the geometric vector in R2, but you can also write it as a coordinate vector. So which one's better? It depends on the context, but usually it's much nicer to work with coordinate vectors because the operations are much simpler to compute, as we'll see by the end of this page. But geometric vectors are also really, really important because understanding how geometric vectors understanding how geometric vectors work in terms of addition, subtraction, and scalar multiplication really helps you reason about vectors and solve vector problems. When you go to do the calculations and work out the details, then it's more useful to be working with coordinate vectors. So that tells you now how you can convert any geometric vector into a coordinate vector. But what if you have a coordinate vector in R2 or R3? Must that always be equivalent to some geometric vector? Like, for example, if I start with a coordinate vector in R2 or R3, is it necessarily the case that there's some geometric vector that I could have started with that that I could follow this process and end up with the coordinate vector that I started with? And the answer is yes. And here's how you can obtain it. So let's go through this note in detail. So coordinate vectors in R2 or R3 are also geometric vectors. So it works both ways. Right, up here we said that geometric vectors in R2 or R3 are also coordinate vectors. Well, this is saying you can go the other way. If you have a coordinate vector in R2 or R3, you can write it as a geometric vector. But in order to do so, you have to come up with an initial point and a terminal point. And I'm going to show you how to do that now. So, and I'm only going to show you how to do it in the case of a coordinate vector in R2, but it's the exact same for a coordinate vector in R3. So let's say you had a coordinate vector in R2. That means you have 2 coordinates. You have the first coordinate and your second coordinate. Well, how can you express this as a geometric vector? Well, we need to come up with an initial point. Let's start with that. So we can write this vector x, right? We can still use the same notation because it's still the same vector, but we're just writing it as a geometric vector now. So your initial point is always going to be taken to be the origin if you're following this method. So you just take the origin to be your initial point, and your terminal point, just take it to be this point P down here. And notice that this point P, we'll points in R2, they have an x coordinate and a y coordinate. Just take the x and y coordinate of this point P to be exactly what the coordinates of the original coordinate vector were that you started with. And that's a perfectly reasonable terminal point. So now we have an initial point of the origin and a terminal point of this point P, which is obtained just by taking exactly the coordinates of the vector you started with. And if you form that geometric vector, now that gives you a way to express this coordinate vector that we were originally given as a geometric vector. This makes a lot more sense if you look at the picture. So let's take a look at what's actually happening here. If I draw a picture of this, well, we're talking about a case in R2 here, so let's draw the xy plane. So we started with this coordinate vector x1, x2. So let's label those on the x and y axis respectively. So x1 goes on the x-axis, and x2 is really, if I were to interpret this as a point like we're doing down here, well, the second coordinate is really a y coordinate, so I'm going to call this x2 up on the y-axis, and there's a point now in the Cartesian plane that has those coordinates, and we're going to call that P. That's really what's happening down here. So call this point P, and we also have the origin down here, right? You always have the origin in the Cartesian plane. It's the place where the two axes intersect. Really, it's the point in the Cartesian plane that has an x and a y coordinate of both equal to 0. Now if I draw the vector that starts at the origin and goes to P, this is what you're getting here when you write this down. Okay, so really what you're doing is you're turning a point in R2 into a vector in R2 by just interpreting this point or converting this point to be just treated as if that point were a terminal point and you have the vector going from the origin to that point. So that's really what's happening. When you take this coordinate vector and you convert it to this geometric vector, you're essentially just taking this point and converting it into this vector. So, but that's how you can turn coordinate vectors into geometric vectors. It's not going to be any different in R3. If you're given a coordinate vector in R3, well then you'd have 3 coordinates here, which means when you write this point down here, you'd have 3 coordinates, x1, x2, and x3. Just interpret those to be the x, y, and z coordinates, plot that point in R3, draw the geometric vector that goes from the origin to your point P that you defined, and the picture will be a 3-dimensional picture, but it's the same principle. Just take the vector geometric vector from the origin to this point, and that's going to give you your conversion method. So the upshot here is that coordinate vectors, if you are in R2 or R3, they're also geometric vectors. And geometric vectors are also coordinate vectors. So if you are living in 2 or 3 dimensions, coordinate vectors and geometric vectors are exactly the same thing. They don't give you anything, neither of them gives you anything the other one doesn't. They just give you alternative points of view, and they give you just different options. Depending on the context that you're working in, just give you different options and approaches that you can take. But if you are in any dimension that's higher than 3 dimensions, so if you're in 4-dimensional space, 5-dimensional space, or anything higher than that, well, now you really only can use coordinate vectors. Geometric vectors won't help you because they only work in 2 and 3 dimensions. So that's where coordinate vectors really truly are different. They genuinely give you more than geometric vectors because they work in higher dimensions as well. So with that in mind, in that sense, coordinate vectors are superior in that sense because they give you more to work with. So now for the moment we're going to shift our attention to working with coordinate vectors. And we talked about the basic arithmetic operations, so addition, subtraction, scalar multiplication. We talked about that in the case of geometric vectors, but now we're going to look at how to do that with coordinate vectors instead. So let's see what we've got here. So we've got a vector x, and it's got how many coordinates? x1, x2, all the way up to the very last coordinate, xn. And then we've got our vector y, which is written in the same fashion. We've got y1 for the first coordinate, y2 for the second coordinate, all the way up to yn for our very last coordinate. And so this is just 2 general vectors in Rn, where n, and I could, if I wanted to be specific, I could say let n be some positive counting number, right? But that's not necessary to say anymore. It's automatically the case, right? If you're talking about Rn, you're just talking about Euclidean space for some particular value of n. So it could be n equals 2, it could be n equals 3, it could be n equals 100, but it's just some positive counting number greater than or equal to 1. So I typically won't say this at the beginning of statements like this, but for now I will. And let's say we also have some scalar value k. Okay, so we can define the arithmetic operations in the following way. So the first one we're going to define is addition. And it's actually easier to define addition for coordinate vectors than it is in terms of geometric vectors, because you don't have to draw a diagram. You can just write down the definition explicitly. So if I want to add these two vectors, x and y, I get the following. So the first coordinate of x plus y is just going to be the sum of the first coordinates of x and y. So just take x1 and y1 and add them together. And that's going to give you the first coordinate of x plus y. Now the second coordinate of x plus y, you might be able to guess at this point, but if not, here I'm going to tell you, just take the second coordinate of x and the second coordinate of y and add them respectively. Okay, and then just carry on in the same fashion. So you'll carry on in that same pattern. The third coordinate of x plus y would just be take the third coordinate of x and add it to the third coordinate of y, right? And then put those together, and that'll give you the third coordinate of x plus y. Carry on in that same fashion all the way to the very last coordinate. So the nth coordinate of x plus y, so in other words, the very last one, just take the nth coordinate of x and the nth coordinate of y and add those together, and you get xn plus yn. This should very much feel like addition of matrices. You're just doing this coordinate-wise or entry-wise, right? If you were to add two n by 1 matrices or add two 1 by n matrices, what would you do? You just add them entry by entry. That's kind of exactly like what we're doing here, except we're just doing it in a different notation. But that's the definition for vector addition. What about vector subtraction if I want to subtract the vector y from x? Well, just do the same sort of approach. Just do it coordinate-wise. So if I want the first coordinate of the vector x minus the vector y, just take the first coordinate of x and subtract the first coordinate of y. So just take this entry here, x1, and subtract y1. Right, in the second coordinate, just do the subtraction, but in the second coordinate of the original vectors. So x2 minus y2, whatever you get, that's going to be the second coordinate of x minus y. And then just carry on with that pattern until you get to the very last coordinate. And to get the nth coordinate of x minus y, just take xn and subtract yn. So you'll get xn minus yn. All right, now what if you want to multiply a vector by a scalar? Well, we've already talked about how to do that for geometric vectors in R2 or R3, but what about coordinate vectors? How is it going to work? If let's say I wanted to take this vector x here and multiply it by this scalar k. Well, what's going to happen? What am I going to get? And it actually is going to be exactly the same as what I would get if I were to multiply a matrix by a scalar. Right? If you were to multiply a matrix by a scalar, the effect that you're going to see is that every entry in the matrix is going to get multiplied by that scalar. But in this case, instead of entries, we have coordinates. So we're just going to multiply every coordinate of the vector x by the scalar k. So just multiply each of these coordinates by k. So the first coordinate of kx is just going to be k times the first coordinate of x. The second coordinate of kx is going to be k times the second coordinate of x. So k times x2, and so on, all the way down to the very last entry. The nth coordinate of kx is just going to be k times the nth coordinate of x, which is this xn. So we'll have k xn. So that is scalar multiplication. Now this fourth property here, it's a specific, part of it's going to be a specific case of the third property, but it's also going to simultaneously introduce some new notation that probably if I didn't say it, if I didn't explicitly say this, you would have guessed it anyway, but all the same, I'm still going to write it down. If I were to write down something like negative x, we never actually defined this for geometric vectors, and nor do we define it yet for coordinate vectors, but I'm going to define it right now for coordinate vectors, and it just turns out that the definition is exactly the same for geometric vectors. So if I took a coordinate vector and I just put a negative symbol in front of it, what I'm really doing is writing negative of the coordinate vector x. And you might be able to guess this, but nonetheless, I'm just going to say it once and for all anyway. Really, all this means is just the scalar -1 multiplied by x. And that's exactly what you do with geometric vectors as well. But what's that going to give you? Well, if you go by now the third definition here, if I have -1 as my k, -1 times x is just going to multiply each of those coordinates by -1, if you just follow the definition given in the third line here. So really what this is going to be, it's going to be the first coordinate of x multiplied by -1, so you're going to get -x1. Then you'll have the second coordinate of x multiplied by -1, so you'll have -x2, and so on, right, all the way down to the last coordinate, which is also going to have a negative in front of it. So that's what it means to put a negative sign in front of a vector. You're really just multiplying it by the scalar -1.